In this video lesson, we're going to be looking at how to represent enthalpy change. So there's 4 different ways that we can communicate the change in enthalpy for a reaction. To do this lesson, you're going to want to take your page and create a very large chart that looks something like this. The first method of representing enthalpy change is simply just using a thermochemical equation with the energy term included. When you have an endothermic reaction, the energy is absorbed like a reactant. So as you can see in this example of the electrolysis reaction, right here, water plus 285.8 kilojoules of energy results in hydrogen gas and half an oxygen gas. We haven't talked really about having coefficients that are 1/2 yet, but we will. The main idea here, though, is that if you are including the energy term in an endothermic reactant, you write it like it's a reactant because the energy is absorbed by the system like a reactant. The opposite is true for an exothermic reaction. If you consider an exothermic reactant releasing energy, it's kind of like the reaction is producing energy like a product. So you then write the amount of energy as a product in the reaction. The second method of representing enthalpy change is writing a thermochemical equation with a delta H value after it. For our endothermic reaction, if we look at the same reaction as above, instead of including the energy term as a reactant, we just write it after the reaction with a delta H equals right here. For an exothermic reaction, do exactly the same thing, except notice that because it's exothermic, the delta H is negative because the system has lost energy. So you can tell if your reaction is endothermic or exothermic based on if the sign in front of the delta H value is positive or negative. The third way we're going to look at is a potential energy diagram. A potential energy diagram looks like this. It's a graph, a representation of what happens to the energy as the reaction proceeds. So on the y-axis is potential energy, so EP, and on the x-axis is the reaction progress. In a endothermic reaction, in a reaction where the system has absorbed energy, the reactants are down here because they do not have a lot of energy. But as the reaction progresses, it increases in energy, and the products have energy up here. The difference in energy between the reactants and the products is the delta H value. So when we draw these for a specific reaction, so we're going to look at our electrolysis reaction, you actually write the reactants and the products and the energy value. So if we were doing it for electrolysis, we would actually write in liquid water up here, and here we would write hydrogen gas plus half an O2 molecule, and we would write delta H equals plus 285.8 kilojoules. And I just realized I've made a big mistake up here. Oh no, never mind. I did not. So that is a potential energy diagram for a endothermic reaction. The potential energy diagram for a exothermic reaction looks basically like the opposite. So instead we have our reactants with a high amount of energy, and our products have significantly less energy because the energy has been released. So when we do this for a actual reaction, we don't write the words reactant and product. We write what the reactants are and what the products are. So we look at the example of magnesium that we've been working with. So we put our magnesium, solid magnesium up here, plus half an oxygen is going to make solid magnesium oxide down here. And our enthalpy value is negative 601.6 kilojoules. The fourth way of communicating enthalpy change is using something called standard molar enthalpy of reaction. So standard molar enthalpy of reaction is the energy change associated with 1 mole of a substance, but at standard atomic temperature and pressure. So usually 100 kilopascals and 25 degrees Celsius. So the symbol for standard molar enthalpy of reaction is still delta H with an X to indicate what kind of reaction it is, except now we put a little superscript 0 here to indicate that it's at, this means that it's at standard atomic temperature and pressure. The standard molar enthalpy values for an endothermic reaction are positive and for an exothermic reaction are negative. When you have to be careful is that if you are given the standard molar enthalpy of reaction, that is the energy change associated with 1 mole. But if there's more than 1 mole involved, you have to do some division to figure out the molar enthalpy of reaction. So we will do some practice with standard molar enthalpy of reaction together. But other than that, this concludes our lesson when we are looking at how we can represent enthalpy change in 4 different ways.